Okay, category terms are very nasty sometimes, and they call something an index category when it is not a category. It's a functor. It's a functor from the top to the basis. But on the other hand, on the bottom, we have things that are simple. They are just context. So it's just x1 of type net, x2 of type bool, x3 of type reals, whatever, right? So that's what's happening down here. What happens on the fiber is where you put your logical structure. So let's kind of think about it together. So the objects are contexts, and the morphisms between the contexts are substitutions, because that's the essential thing that you need to do, right? You need to be able to say, this x here is actually going to go to this y here, and that that transformation of the context x1, x1 to y1, y2 is a morphism. It's a morphism. And the structure of this base is a parallel composition that we are looking at in a minute ago. The terms for each context gamma down there you define a category, as I was saying, D of gamma, because the D is kind of taking the rectangle to the line. And these things are, the category has variable type pairs, and morphisms are the terms that we've been playing with all this time. And the fact that we do the substitutions on the bottom is what makes this re-indexing work. So the traditional way of thinking about this is so it's an index category, so it's a functor from COP to cat. And as I was saying, it's a bit of a misnomer, but that's how everyone does it. There's a little bit more of, I am simplifying, as you might expect, but I think you get the basic idea. That's what people normally do. Now, actually, and I should at least give you the reasonable equations, the reasonable way of rewriting this stuff, right? So we're going to say that because we have this category of context here, we can do the extension, the composition of substitutions works as we know and love, right? We have identities for both sides and associativity of the composition on the base and functoriality of the defunction that takes this, the band to the basis. And so we have associativity and composition functionality of the D and and the projections as you expect. Now, how are we going to change that? How are we going to change that to deal with things that are linear? Because, you see, the way we've been discussing, this guy's here, the basis, does two jobs. It composes the substitutions like we said before, but it also does, as we also mentioned before, product of types. And now, if I want to be linear, I don't want to have products of types. I want to have tensor products, and I cannot have projections, because if I have projections, then I'm not linear anymore. Sure.
What's the difference between products and tensor products?
Very good question. The main difference is exactly the existence of projections and diagonals. So a tensor product is just an operation that glues things together, but you cannot just disintegrate them. You cannot do P1 and P2 like we've been doing all the time over here. Yes, so, that's where the linearity bites in, because what you want to do for linear functions is this business of if you have A, linear implies B. Also, A, that will give you the B. But as I say, you cannot project and have this guy or this guy. They have been used. So you cannot have projections, because if you have projections, they would be repeatable as many times as you wanted. So problem number one is that this picture that I was showing you here is very nonlinear. So the identity in the fibers require judgments of this shape, which are judgments that are not very linear, because you have all the gamma that you have to get rid of. And the problem number two is that we have no syntax at the moment for forming substitutions from the terms, which is a little bit harder to see, but take it for the time being. So the way we kind of solved the problem that many years ago was by constructing this sort of categories that are context handling categories. So instead of having an index category, which is, as I was saying, this complicated bit of mathematics, but it's very well-established mathematics. It's been going on for, not only 20 years, but more like 50 or 60. But we can change it. And instead of having, as we had before, a D from COP to cat, and cat has to have identities, right? It's the only thing that we have been banging on about. It have to have identities and have to have composition of morphisms and associativity of the composition. So we change this cat into set to T. So maps from the set of types T into set. Don't force the existence of the identities. And then you have to do something more complicated. I mean, simply removing structure won't do us too much, right? So we have to do this business of creating natural transformations that will explain how the substitution works. And sorry, this definition is me trying to be too clever by half and doing both the linear and the Cartesian side by side. So the linear, you have a factor L from P op, P is the base again, into set to the T, and we have to have this natural isomorphisms between terms and substitutions. And the Cartesian is just where you read, So the cleverness here is to say, okay, I still have some products on the basis because they are just how I'm putting together my substitutions. But what I need to kind of think about the structure of the logic is in the fibers. And what I know is that to be linear on the fiber, I just need an SMCC, a symmetric monoidal closed category. And what is to be Cartesian in the fiber, I need a CCC. So each one of the fibers for a Cartesian handling category is going to be a CCC. But for a linear category, it's going to be an SMCC. So no products in the fibers, products on the basis for the linear case. Products in the fiber and products in the base for a Cartesian handling category. And you need to use the Yoneda lemma. That's why lots of people love it so much, to show that the whole thing works. Then you have natural equations. So, applying substitutions F to the term T is the same thing as kind of introducing an extra term for X, composing with the other substitutions that you had. And the two versions of making these guys isomorphisms between themselves. And okay, it is hard to understand in one go and like that. I'll have to let you think about it and ask me questions tomorrow or today if you want. But believe me, it works. So you have L categories and you have E categories. The E categories are the Cartesian ones and the L categories are the linear ones. And the cleverness here is that these E categories are just the instantiation of Earhart's D categories for the simple type lambda calculus. Sorry, for the dependent type lambda calculus. So we are recovering stuff that had been done before. And now we do have that the contexts are isomorphic the way we want for the Cartesian version, for the versions that are traditional intuitionistic logic. And, okay, I really should explain this properly, but I don't think I can. So I'm going to just say that the category theory is really guiding the design of the calculus, because you are just trying to see how to do substitution using this kind of complicated categorical structures. But as I was saying, the point is that for the E categories, which are the Cartesian ones, you have the ISO that you expected. But for the L categories, which are the linear ones, the tensor does not give you an ISO, it just gives you a way of moving from morphisms from into A to B, into morphisms into the tensor, and vice versa. I'm sorry. Now, this is kind of cool because you actually can do proper linear logic. You can't just do the things that have no bands. And doing the bands is easier because you take your L cats and your E cats, and as you can see, the E cats have proper function spaces, products, and unity types, like we have been discussing all these 2 days, whereas the L cats have linear function spaces, tensors, and I types. And the way to deal with the bang constructor is to have a monoidal adjunction between the E cats and the L cats. So a bang L category is a monoidal adjunction where C is an E cat, B is an L cat, and the monoidal adjunction preserves types. And, you might recognize the little blank there, which is similar to what Brigitte was saying earlier, about early on, because dealing with modal logic is very much similar to dealing with linear logic. So we end up with quite a few theorems. We end up with a theorem saying that the definition works as expected, meaning that an E cat contains an underlying CCC, so you get rid of all the explicit substitutions and have just the terms as you expected to have. You have soundness, because we can prove that we model the lambda sigma calculus as we expected. So kind of anything that's the term of the lambda sigma calculus will have a representative in one of these E cats. You have completeness, and categorical completeness is a little bit of a funny thing, because a completeness here is the way I'm writing it there. So for any E cat, if you have two morphisms in the lambda sigma calculus, and they have the same domain and codomain, then the equality of these two morphisms is proved in the theory of of the lambda sigma calculus. So, and you have the same sort of three theorems for the L categories, that is for the linear case. And to do the bank, we just have to use one slightly different version from the calculus that we've been discussing for modal logic and for linear logic. So it's as a variation of the calculus that I discussed yesterday, but this variation kind of, you have to add to this, I mean, same way as we kind of trying to add to lambda here, the split substitutions, we start from our linear lambda calculus and we add the split substitutions exactly the same way, so exactly the same steps. We create the substitutions, you kind of, you create your big models, you think about your SMCCs, and everything works. So, and that is what I call Barber's dual calculus, because he actually proved with all the details that this calculus satisfies all the conditions that we needed to satisfy. So, normalization, subject reduction, alpha conversions, and everything else that we need. Sure, please.
When you said the right definition theorem, does it mean that there's the junction between E categories and vertex closed categories or equivalence?
Sorry, say it again, because the basic idea of the models for linear logic are that you need to have this operator that says that everything is back to normal, right? In the linear logic case, you don't have products, you don't have diagonals, everything is used exactly once. You put this bank, and that kind of can be seen as a half of an adjunction, a monoidal adjunction between the classic category and the category. So far so good. So what was the question?
In the previous slide, you had in the first part, you said that every E category is an underlying Cartesian closed category, and for every Cartesian closed category, you can create E category. Is this an equivalence?
Yes. Both for them. It's an isomorphism more than an equivalence. I think I kind of want to quickly over it, but you see, every ECAT contains an underlying CCC, and every CCC can be extended in an isomorphic way to ECAT. And so, yes, thanks for noticing this important point. It's not just forgetting the information, but it's forgetting the information, forgetting that you had the extra substitutions, but also being able to bring them back, right? Saying that we have, it's proving that the underlying stuff is exactly what we needed to have. Thank you. Sure.
Does this mean that the lambda sigma calculus is equivalent to the standard lambda calculus? If the lambda sigma calculus is modeled in the ECAT,
Yes.
which is isomorphic to the Cartesian code category, which is
It's not the CCCs, right? Because it's only simply type lambda calculus.
Yes.
Whereas the L categories will be modeled in an SMCC because they have to be linear, they have to use the arguments completely.
Okay.
And then the point is actually putting the two together, because the model of linear logic without the bank is very weak, doesn't do anything for you. So you want to be able to, as I was saying, whenever you want to be linear and know where things are being used, you're linear. But whenever you say, I don't care, you go back to intuitionistic logic. So then you need to have this monoidal junction between ECATs and LCATs, because they are the ones that kind of keep the substitutions, but do, in terms of logic, in terms of real meaning, do exactly what you expected them to be doing before, right? So simply type on the calculus and linear type. but thanks, because it's, you know, sometimes it's hard to kind of remember to say all the important bits. So, like, the ISO was there, but, you know, I just went through it, right? Okay. Because I've been such a horrible person and not explaining to too many of the equations, I think I might end too early and then might kind of go back or ask if you want to ask questions, you're very welcome. But let me kind of go over conclusions and then we'll see how it goes. So what I'm saying is that index categories are inherently nonlinear, but we can use spreadsheets. The species substitutions are tricky to model because, as I was saying, we don't want them to appear in the final model. We want to have exactly what we're discussing, this idea that once you act on the substitutions, once you affect them, they disappear and you end up in a calculus that's just the simple type Lambda-Calculus and just a Cartesian closed category. But you want to be able to see which ones, you want to be able at the beginning to see what are substitutions and what are real terms. So that's why you need this so-called higher order kind of category, because you have one category here and a collection of categories over there. So the models that we're talking about, they take isomorphism seriously. And some people might say, it's too hard, Valeria. I can't work with this stuff because all this isomorphism that I had, that I kind of conveniently try to avoid, they have to be put into the computer, right? You have to do them somewhere. But, and that's one of the reasons why I put this sentence there, but on the other hand, if you use your De Broglie types, then the computer takes care of them for you. You don't have to do it yourself. You know, people have had this technology in place for a while. And, you know, this is an extension of the Curry-Howard, more complicated extension, but actually, you know, it's actually very simple compared to the extensions that we need for the dependent types. So, you know, you can use that as a stepping stone to get there, to actually understand the different semantic characterizations of the dependent calculi, kind of bit by bit. And I have tried to show you very quickly, but you know, you can read, because we have working index category models for linear, Cartesian, and both, as well as the one for the calculus of constructions, but without universes, also so far. And I think this kind of shows that explicit solutions are not simply a hack. They actually are theoretically important. And if they weren't, we wouldn't be able to have a type theory with all the properties that we have for them. So, I mean, there's an awful lot that I didn't go over because it would be lots more of syntax that I get confused when I try to discuss. But there are papers on that. So when people discuss which kind of explicit substitutions they should have, they discuss things like, do you need equations in context or raw reductions? Do you need De Broglie indices or variable names? Do you need untyped or typed calculi? Do you need calculi for abstract machines or for proof assistance? So all these choices kind of, we discuss all of them, and we think that actually all of them have a kernel of truthness to them, which kind of, you know, it doesn't really matter if you kind of discuss your, I mean, I think by now, most people prefer to discuss equations in context versus equations that are just without the context in. I think the contexts are helpful. And I think, when you talk between De Broglie indices or variable names, actually, I cannot read the De Broglie number, even if it hits me in the head. So I think, for humans, the names are much better, but for the computers, it looks like the indices work fine and actually are slightly more efficient. Typed versus untyped, it's again the usual stuff. You can do untyped if you want, but for some properties, you're much better off with the typed. And so the whole of the calculi that I'm kind of trying to discuss with you have been driven by the correspondence with the categorical semantics. And one of the things that people say about the lambda sigma is that it's not a good calculus, as I was mentioning before, because it doesn't satisfy strong normalization. But strong normalization might be asking too much, because there are different in different evaluation strategies. And as I was saying here, there is a paper written by himself that shows that every reduction used in abstract machines terminates. So you don't need a strong normalization in your calculus so much, perhaps. That one I don't even know where I stand. I'm just repeating what I've been told. And I think the question that I have for you guys is, which other logics can we do? I mean, I know we can do CS4, but there's loads of other logics that I have no idea. All the difference between different dependent types, I don't know. As I say, I only know how to do dependent types without universals at the moment. And, kind of, how far can we take this idea of extending the Curry-Howard and extending checking what are the main properties that we want of a Curry-Howard something. This is all kind of exciting work for young people to think about and get working and do the calculations for, right? Because these calculations are not a triviality either. So, I think, I'm kind of very much willing to talk to you guys, but I think I'm going to, so final conclusions. So all 3 lectures are about categorical Curry-Howard. There are several systems and many trade-offs. Some of them I presented, some I have not. I think I only scratched what category theory can do for you, right? I mean, as I said, there's all this stuff about fibrations. There's this thing about index categories being a kind of a fibration, a simpler kind of a fibration, but there's an awful lot more that you can learn about on category theory. And the homotopy type theory that Anya is going to talk at some stage, it's completely, and Paige is going to talk about. It's kind of very exciting, and it's much harder category theory than the stuff that I try to present. And I think the thinking along these lines of using the Curry-Howard both in the direction from logic to type systems and from logic to category theory and the backwards direction, kind of looking at the type theories that are invented by people for implementations and then trying to think of them as theory, both directions are very helpful and provide benefits both, to logic, to category theory, and to software that we're trying to prove correct by construction. So, as I was saying before, I think we need more interaction of communities, and with that, I think I'll say that we can have lunch. Oh, not lunch, coffee, no coffee.